You're looking at two houses with the exact same floor area. One has a low, minimalist roof, and the other has a soaring, dramatic gable. From the outside, the difference is just style. But on the inside, that single decision, the height and pitch of the roof, has created two entirely different buildings from an engineering, comfort, and cost perspective. A high roof isn't just an aesthetic preference, it's a massive commitment that changes the physics of your entire structure. So, how do you decide what's right for your project? In this video, we're going beyond the pretty pictures to uncover the real-world implications of roof height. We'll explore how it dictates your structural system, controls your energy bills, influences the feeling of your space, and hits your wallet. Whether you're an architect sketching concepts, a builder advising a client, or a homeowner dreaming of a light-filled great room, understanding these principles will ensure you make an informed choice, not just an emotional one. Let's start with the most immediate and tangible effect, the creation of volume. A high-pitched roof with a cathedral or vaulted ceiling fundamentally changes the spatial experience of a room. It feels grand, open, and liberating. It allows for the strategic placement of clerestory windows, those high vertical windows that flood a space with indirect, glare-free natural light. A key principle in passive solar design. This can create a beautiful, ever-changing play of light throughout the day. However, this volume comes with a direct physical consequence: cubic footage. You are now heating, cooling, and dehumidifying a much larger volume of air than you would in a flat-ceilinged house with an attic. That attic, often forgotten, is a crucial thermal buffer. It's a layer of stagnant, insulated air that separates your conditioned living space from the extreme temperatures of the roof deck. By removing the attic and exposing the roof structure, you eliminate this buffer, placing your interior space in direct contact with the roof surface, which can be scorching hot in summer and freezing cold in winter. This is the first major trade-off: spatial drama for increased environmental control challenges. Now, let's talk about the structural implications, because this is where the cost and complexity can skyrocket. A standard, low-pitched roof on a typical house is often built with pre-engineered trusses. These are incredibly efficient, lightweight, and span long distances with minimal internal support. They are a factory-made system designed for economy and speed. However, when you want that open, vaulted interior space, you can no longer use standard trusses because their webs would be cutting right through your living area. You have to switch to a different structural system. The most common alternatives are structural ridge beams with rafters or large, custom-designed scissor trusses. A structural ridge beam is a hefty, often steel or large timber member that runs the length of the roof's peak, supported by columns or walls at each end. The rafters then hang from this beam, creating a clear span below. This is a pro-level system that requires precise engineering calculations for the beam size and the connections. The cost of that single ridge beam, plus the labor for its installation, can be many times the cost of an entire truss package for the same area. A common and costly drafting mistake is to underspecify the supporting posts or walls for the ridge beam, leading to dangerous structural loads down to the foundation. The efficient workflow secret is to involve your structural engineer during the earliest conceptual design phase, not after the aesthetics are finalized. One of the most powerful, yet often misunderstood, effects of a high roof is on the building's thermodynamics and ventilation, specifically through a phenomenon called the stack effect. Hot air rises. It's less dense than cold air. In a space with a significant height difference, this creates a natural convection current. The warm, buoyant air accumulates at the high point, and if you provide an outlet like a ridge vent, an open clerestory, or an operable skylight, it will escape. As this hot air escapes, it draws in cooler, fresh air from lower openings on the opposite side of the building. This is passive, natural ventilation, and a well-designed high roof can harness it to significantly cool a building without a single watt of electricity. This is a cornerstone of bioclimatic architecture. However, if this effect is not managed correctly, it becomes a liability. In the winter, that same rising heat will sit against your highest roof surface. If your insulation and air sealing at the ceiling line are not absolutely perfect, and I mean perfectly installed, and continuous all that valuable heat you paid for, will simply leak out into the great outdoors. A pro tip from building scientists is to create an invented conditioned attic assembly for cathedral ceilings where the insulation and air barrier are applied directly to the underside of the roof, sheathing effectively bringing the entire space inside the thermal envelope. This is a more advanced but highly effective detail. This brings us directly to the critical topics of energy efficiency and insulation. How you insulate a low-slope roof versus a high cathedral ceiling is completely different. A low-slope roof with an attic is straightforward. You dump thick batts or blow cellulose onto the flat attic floor. It's easy, cheap, and highly effective. Insulating a sloped cathedral ceiling, however, is one of the most challenging details in building envelope science. You have a limited depth between the interior drywall and the roof sheathing. You must fit enough insulation to meet code R values, but you also must leave a vital air gap for ventilation to prevent condensation from rotting your roof from the inside out. This complex assembly of air barrier, insulation baffles, and ventilation channel is where most failures occur. Compromising on any part of this system can lead to catastrophic moisture problems and mold. Furthermore, the increased surface area of a high-pitched roof means there's simply more roof exposed to the sun, rain, and wind, which can accelerate wear and tear on roofing materials and increase the initial cost of those materials. Finally, we cannot ignore the impact on acoustics and cost. Acoustically, a large, hard, sloped ceiling surface can be challenging. Without the sound-absorbing qualities of a flat acoustic tall ceiling, sound waves can travel unimpeded, leading to a noisy, reverberant space. Think of the echo in a large barn. This might be desirable for a music room, but terrible for a peaceful living area. Strategic use of rugs, drapes, and fabric wall hangings is essential to tame the acoustics. And then there's the bottom line, cost. A high, complex roof is exponentially more expensive than a simple, low-pitched one. The reasons are cumulative: more complex engineering, more materials, larger structural members, more sheathing, more shingles, more labor for framing and detailing, and higher long-term energy and maintenance costs. It's a significant investment that must be justified by the design vision. To summarize the key takeaways: 1. Roof height is a trade-off between spatial drama and thermal energy control. 2. Moving from trusses to a clear span system is a major structural and financial leap. 3. Harness the stack effect for passive cooling but guard against it in winter with impeccable air sealing. And 4. The insulation and ventilation of a cathedral ceiling is a high-stakes detail that demands perfect execution. Now I want to hear from you. In the comments below, what's your biggest challenge or lesson learned with a high or low roof project? Was it managing the cost of the structure, solving a condensation issue, or making the energy model work? Your real-world stories are invaluable. If this deep dive into the physics of roof height was helpful, please give this video a like and subscribe to Architect AI for more content that turns architectural design into applied science.